Hello, welcome to the lecture series on vehicle dynamics. In the previous video, we have discussed about the steady state handling, how exactly the weight distribution, the front and the rear, and also the tire cornering stiffness affects vehicle handling. In this session, let us talk about the suspension effects on handling. So under this, let us consider roll moment distribution, camber change, roll steer, lateral force compliance steer, aligning torque, and tractive forces. First, you know that many things we have already discussed. In a suspension, you will have a roll center. If the center of gravity is above that, if there is a force at the center of gravity acting outwards, and that force went to this distance, we call it as a roll moment. So you will have, for the front suspension, you will have a roll center. Rear suspension also you will have a roll center. If I join front roll center and rear roll center, we will get the roll axis. Correct. As the suspension moves up and down, you can also see that the roll center is also moving up and down. So it's a dynamic thing. So now body roll. So when thinking of load transfer, it may help to consider body roll. As the body rolls, the outside springs are compressed and place more load on the outside tires. So we have studied this. If you have spring mass like this, and these are the suspension springs. Okay. Suppose the vehicle is taking a turn like this. This becomes inside and this becomes outside. Okay. As the body roll, the outside springs are, because when you are taking a turn, the load gets transferred like this. So the outside springs are compressed. These springs are compressed. Correct now? So that there will be more load on this. So here Fz plus some dynamic load will be there. Here Fz minus the dynamic load. Okay, right. In reality, body roll is a result of cornering force, not a cause of load transfer. Okay. If you double the spring rate, you will not significantly change the load transfer, but you will reduce body roll. So result of cornering force. Okay. I have told you what exactly a cornering force is already. So I told you about this, and you are going to get an angle here. Initial position to now. This is what you call it as the roll angle. You know that. We have learned about it. Okay. If the lateral force we are talking about happens on the front wheels, then the vehicle understeers. If it happens on the rear wheel, then the vehicle oversteers. That also I think I will explain there. So this is the center of gravity of the front portion, center of gravity of the rear portion. Let us say this, the overall center of gravity is here, and you have a force like this when you are taking a turn this way. Correct. This is W by G. You call it as WF by G V squared by R. Next here it is W R by G V squared by R. Correct. If this is greater than this fellow will turn like this. This is greater than this, then it will understeer. This is greater than this, then it oversteers. Okay, if it happens on the rear wheel, then the vehicle oversteers. Roll moment distribution changes vehicle handling characteristic. If roll moment distribution is high on front axle, the vehicle understeers. It oversteers if the roll moment distribution is high on the rear axle. Right. Auxiliary roll stiffness alter handling characteristics. Stabilizing bars we call them. Using stabilizing bar, the roll moment on the front can be increased, thus making the vehicle understeer. Using stabilizing bars at the rear, increase the roll moment on the rear side, making the vehicle oversteer. This is how we use the stabilizing bar, anti-roll bar, like this. So roll moment distribution, I think this I have already explained under roll topic. Okay, vehicle is taking a turn like this. There is a centrifugal force. There's the roll center over here. Now this will roll. Load comes on this spring. This compresses and this stretches. This fellow will offer a resistance in this direction. This fellow will pull this. Alright. So that's how we have brought in something like, the concept of roll moment. K5, where K5 is called roll stiffness. That is nothing but this one, where the stiffness of the suspension spring is important. Also the distance separating these two is also important. So K5 is this and phi is the roll angle. So lateral load transfer, then what is now FZ0, FZI we can find out. So taking moment, this also we are done. Okay, taking all these moments we will get this. Finally the difference in load, vertical load, is this plus this. This we call it as load transfer due to cornering force. This is the load transfer due to vehicle roll. These things we have already studied. Fine. Now what is the roll angle? Let us calculate roll angle. I have taken one point on the roll axis. This is the centrifugal force. About this point I have taken the moment. Then the weight into this distance, that is what you have taken, WH1 by phi. This is also clockwise moment. And of course you have roll stiffness from here and this suspension that is acting in the counterclockwise direction. By equating these two, I get phi, the roll angle. Okay. Right, sir. So once you got the roll angle, okay, this is the one written. Roll rate is just differentiate with it respect to lateral acceleration, you will get the roll rate. Roll moment at the front is roll stiffness into roll angle. This is the roll moment distribution due to load transfer. This is due to cornering force. Okay, that is nothing but this value. Similarly, on the front side, this is the roll moment distribution on the rear. I told you there are two types of load, rolling load and another one is cornering force. And this is the load distribution on the rear. This is roll moment distribution. Okay, now I told you about C alpha. C alpha is what? Tire stiffness coefficient, cornering coefficient, tire cornering stiffness. I call this as alpha. Okay, this is a tire slip angle, this is a lateral force. So lateral force is equal to, I should have written C alpha F here, alpha F here, alpha F here. FYF should have been C alpha F into alpha F. But I have considered the second order effects have actually, if I start expanding this, it will be in this form. Second order effects I have considered, and that's what this part has subtracted. Okay. So this lateral force must be equal to tire grip force, or lateral force at the tire must be equal to centrifugal force. Same way on the rear side, I can write like this. Is that okay? So now we have got some interesting relationships. You see here. Here we have interesting relationships. So from this equation, let me get alpha F. From the second equation, I'll get alpha R. Is that okay? Now our understeer or gradient or cornering equation is this. Let me substitute alpha F value. Also let me substitute alpha R value. Is it okay? C alpha is very much greater than this kind of a thing. So this one I can approximate like this. Okay. Let me approximate this. This only jugglery. Substitute into this, then reorganize. When you reorganize, you are going to get two parts. 57.3 L by R. Here you are getting one part and you are getting another part. Correct? No? And V squared by GR is nothing but AY. And this one we can call it as understeer gradient due to lateral load transfer. We can call it understeer gradient due to lateral load transfer. We can call it. Okay, that part. Okay, right, sir. So from here we are getting all this. So more load on the front, then this definitely this will be much higher than this. This will become positive. Okay, and also what matters is the tire stiffness at the front compared to the tire stiffness at the rear. Tire cornering stiffness. This is what I am talking about. This is less, then what will happen? This will become more. This is great, this will become less. So better keep the rear tire more, should have higher, okay, tire stiffness, lateral stiffness coefficient, stiffness compared to the front tire. Is that okay? So that we can always increase this value. Tire matters, load matters. Okay, right, sir. In general, roll moment distribution of vehicles tend to be biased towards the front wheels due to to make the vehicle slightly understeer. That's the idea. Camber also going to create problems. While studying camber, I will explain that lateral force versus camber angle. As the camber changes, lateral load also increase. Correct. And that will start pulling. Correct. That makes the vehicle add to the understeer. That's the main thing like this. Right. But however, the influence is not much. Okay. So we can give K camber value by this equation. I have not derived it in detail. I just straight away written down these things. Okay, there is a roll rate. So because of that, definitely there will be a camber change. So then there will be lateral force. So I have considered these things, right? Right. This C gamma, right? You know, gamma is camber angle. C gamma tire camber stiffness, lateral force by gamma. That is nothing but camber angle. Roll steer. So let me explain the figure here. You consider the frame of the vehicle. You consider the frame of the vehicle like this. Yesterday I was talking about trailing arm suspension. Trailing arm. It can be considered as a trailing arm. And also I told you two things, anti-squat and anti-pitch. Anti-pitch bars. To introduce anti-squat and anti-pitch, we'll introduce the bars like this. Now, what is the effect of this? Also, I told you yesterday, okay, leave it. This is the ground. You have the tire like this. And this is your height of center of gravity. Then you join this point. I said you can connect this bar on this imaginary line, any point to the frame, I said. So either you can connect like this, or you can connect like this, or you can connect like this. Correct? These are anti-pitch bars. By chance, if you connect like this, let us say your vehicle is taking a turn. Now load is transferred here. Load is transferred means it gets compressed. Then what happens? Its length has to increase. So your fixed hinged here. Then what it does is it pushes the vehicle like this. Correct? It pushes the vehicle like this. You are steering in this direction, it is oversteering. That's the kind of problem. So suspension roll axis, inclination of suspension roll axis. Okay, this bar was right. So it will oversteer if you connect like this, neutral steer, understeer. So suspension, that is the reason you see here, this suspension roll axis we are talking about here. Another very important thing. So that is the reason roll center at the rear is kept high compared to the front, so that when we can join these two, this will be in this form, it will make the vehicle understeer again. Okay. Okay, lateral rotor. So these are important. When a vehicle rolls in cornering, the suspension kinematics may be such that the wheels steer. Roll steer is defined as the steering motion of the front or rear wheels with respect to the sprung mass that is due to rolling motion of the sprung mass. Consequently, roll steer effects on handling lag the steer input, avoiding roll of the sprung mass. Okay, right. And this is given by this equation. And this epsilon is known as roll steer coefficient. Degrees of steer per degree roll. Okay, what is the delta value, degree of steer per degree of roll? Okay. Okay, there's a reason why this particular roll axis also you have seen drooping down always. Lateral force compliance steer is another thing. Is basically use of soft bushes. You can see here because of the cornering forces, correct, about the air center. So really it will go like this about the air center. This may rotate like this or it may rotate like this. That is the thing, because of soft bushes. So this is what we call it as lateral force compliance steer. Okay, with the soft bushings used in suspension linkages for LVH reason, there is a possibility of steer arising from lateral compliance in the suspension. You please see here, it is not in the front plane, it is about this, yeah, z axis. About this point it will, because of this lateral forces that is given by this one. Lateral force aligning torque I have explained already. So what happens due to the caster angle, this has been explained. What is the effect of positive caster and negative caster, and that aligning torque value, understeer gradient due to aligning torque is given by this. Okay, next, similarly tractive forces, we can derive this one from the tractive forces. Understeer gradient due to tractive forces. If fx, assume that it is front wheel driven vehicle, this is not there, so it is minus, it oversteers, correct now. So front engine front wheel driven oversteers. If this is not there, suppose this is there, this is minus and this minus, it will become plus, it understeers. Right. Okay. On a four-wheel drive, these mechanisms would suggest that the rear axle should overdrive the front axle to ensure understeer behavior. On a four-wheel drive, These mechanisms would suggest that the rear axle should overdrive the front axle to ensure that understeer behavior. That means this value should be greater than this value, then minus minus will become plus. Okay, right. So traction forces, fine. Okay, all these I have summarized, nothing more than that. Now you see, you have got understeer gradient due to cornering stiffness, tire cornering stiffness. Understeer gradient due to lateral load transfer. Understeer gradient due to camber. Understeer gradient due to roll steer. Understeer due to lateral force compliance. Due to aligning torque. Due to traction forces. Steering system. Okay, all these you put together, you will get K value. And you want to make the vehicle understeer, K should be positive. So you have a lot of choices to tune the system. So how much understeer gradient we should have? That is the question. It is very difficult to say exactly this is the value. However, we can test and we can tune the vehicle. But it gives you an idea here. Gives here change in road wheel steer angle. That is delta. This change in steering wheel angle. Steering wheel angle. Let us say theta steering. So this I called it as steering ratio earlier. Correct? No, it all depends on the steering ratio. Because it is a steering ratio versus lateral acceleration is given. Lateral acceleration is AY. So that is nothing but V squared by GR. Okay. So what maximum speed you should manage? What steering ratio? Probably we can get an approximate understeer gradient. This slope you can get. Right. So these are all the things that influences understeer gradient. Now if you think your vehicle is your design, put everything in place when you test, slightly understeer needs to be increased or needs to be, then it will become, your vehicle will become sluggish and you want to make your vehicle little responsive, you would like to reduce the understeer gradient. So which are all the parameters, like which are all the gradients you have to adjust? You have lots of choices, but you have to carefully choose which is the right thing to do, because doing one will affect the other. Okay, with this we'll stop at this point. Next, let us look at what are the vehicle dynamics tests that we can do to find understeer gradient value and also to ensure stability of the vehicle. Let us stop at this point and continue in the next video.